Okay, we'll see how this goes. I had to pause because I had to get my thoughts together for the pressure gradients. So what I was saying is we know that, I'm going to come back to this one for a second, that oxygen at sea level is 159 millimeters of mercury. So pressure gradients. So at sea level, the pressure of oxygen is 159 millimeters of mercury. All right, this is at sea level. Now, even if we just go 3,000 feet, okay, that's not very high, really. I'm thinking of it. Denver is a mile-high city, and that's 1 mile, which is 5,280 feet. So anyway, even if you go from sea level to 3,000 feet, the partial pressure drops from 159 to 110. Okay. So think about this. Normally, at sea level, it's 159 of oxygen coming in here, okay? That's great, all right? But if you just go up a mountain, just gain elevation, the air is more thin, as they say. So at 3,000 feet, it drops from 159 to 110, okay? So we know at 159, when it came into the lungs, that it would drop to 104, okay? And that the oxygen coming around it was 40. If you're at 110 coming in, this could drop to, I don't know, it could drop to 90 millimeters of mercury. So that is not as high as 104. So less oxygen will diffuse across, all right? So then think about Mount Everest, which is, that's 3,000 feet, it's at 110. I don't even know, I'd have to Google it. But at 28,000, that's how high Mount Everest is. There's not gonna be enough pressure of oxygen in the air to cross over, unless you're sure. All right, so basically pressure gradients. At sea level, it's 159. At 3,000 feet, it's 110. Okay, therefore, right here, therefore, less oxygen diffuses across into blood, based on Henry's law. Okay. All right. Sometimes people can be placed in a hyper, H-Y-P-E-R, hyperbaric oxygen chamber. And here they'll subject you to partial pressure. A lot of times they, I think they put like part of your body, like if there's if you have an injury or a wound that will not heal, they put it really high pressure. When I say high, I'm talking about 2,300 millimeters of mercury to maybe 3,000. And this is used, make a little divider here. This is used to treat wounds for anaerobic bacterial infections. Remember, anaerobic means bacteria likes to live when there's no oxygen, all right? But if you blast it with some oxygen, it's going to kill that bacteria. This is used to treat, a lot of times, gangrene. Because this bacteria hates oxygen, you're subject to a lot of oxygen, then a lot can cross the membranes and quickly kill it. But anyway, that's just a side note. Okay, 2, what affects is solubility, as we already know. There we go, solubility of gases. Hope this is recording. Yes, okay, and this is a little bit harder to explain. One thing that I want to get across to you. CO2 hooks on to hemoglobin as well. But we know that, let's just do a quick little review here, scratch paper review. Hemoglobin is 4 globular proteins, alpha and beta proteins. Okay, and also in here we have the heme molecule, and on that heme molecule we have an iron, Fe. I don't know if you can see that, Fe. What hooks onto that Fe is one oxygen molecule. All right, so this right here is one hemoglobin. This will make sense in a minute, okay? Review, 4 globular proteins. This is represented with the green and the blue. Each globular protein contains an iron atom, and each iron can hold an oxygen, okay? So in this case, this one has 4 oxygen atoms, molecules, sorry. Can it hold any more? No, that's as many as it can hold. But the thing is, once it gets rid of the oxygen, let me draw these again. This hemoglobin is going to carry CO2 out. And we've got our heme group, which is, we've got iron in there, okay? All right, we have this deoxy hemoglobin now. Why? Because we don't have any of the O2s, all right? Lost oxygen. The thing is, now this can carry CO2, and the CO2, let's say this is CO2, the green, it doesn't hook on the iron. It just hooks on to the globular proteins, all right? So, and it may actually have an affinity. CO2 is probably more soluble than oxygen. It is more soluble than oxygen. However, due to the pressure gradient changes, remember the pressure gradient changes here? Oxygen was 104 to 40, and CO2 was 40 to 46. See, that's not a huge change for the carbon dioxide. And since it's not a huge change, that pressure difference causes the solubility rate to be a 1-to-1, okay? Don't get lost in that. Don't worry too much about this. I guess basically what I really want you to know about this is that the solubility of gases can affect the gas exchange. And I was just trying to show you that oxygen, a hemoglobin can hold 4 oxygen molecules. However, it can hold more carbon dioxide, but since the pressure gradient is so low in carbon dioxide, it still all equals out 1 oxygen for 1 CO2. So you can have, if you have questions on that, you can talk to me about that. So solubility of gases, so CO2 maybe 20 times more soluble than O2. However, the pressure gradient difference, well, that's what gradient means, keeps the gas exchange 1-to-1. 1 oxygen for 1 CO2. It's a trade-off, okay? Third one is membrane thickness. Remember, we're answering the question, what affects gas exchange? Membrane thickness. So if you have pneumonia, this is the increase of serous fluid because you have an immune response. And if you get all this fluid into the lungs, it can cause edema, which makes the membranes thicker, which is harder for gas to come across. Membrane area can also cause gas exchange to become slower. Why? For example, emphysema. Emphysema destroys alveolar tissue. It may cause it to lose its elasticity, so it's not quite as springy. And also decreases alveolar surface area. So if you have a decrease in surface area, you're not going to have as much gas exchange just because there's nowhere to do it. And the last one is ventilation, perfusion, coupling. This is when, remember I told you the lungs are compartmentalist, what's that word? They're in compartments. I can't think of the word. And so if you damage a section of lung, there's going to be a low pressure of oxygen in that area. This is just common sense. If you mess up part of your lung, of course you're not going to have great gas exchange. All right, so we've done Boyle's, Charles's, Dalton, and Henry. There's one more, Fick, but we're not going to worry about him. Okay. Now, we're getting closer and closer to the end. See, we only have 10 pages, and we're, oh my goodness, where's 10? Where's 9? I need 9. All right. Let's take a pause. Pausing.